Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family: Moreau, Teresa, Chris, Matty, Linda, and Sabrina. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener supported and ad-free for everyone, and it's very much appreciated. As members in the month of May, you and everyone else who serves as a patron will be entered into a drawing at the end of the month. 4 winners will be selected, each of whom will have the chance to choose one of our August readings. It's your turn to choose your favorite, and I can't wait to see what the winners select. If you're interested in being entered into this drawing and finding out more about the perks available to subscribers, including exclusive episodes heard nowhere else, like our current chapter-by-chapter reading of a wonderful classic, The Wind in the Willows, you'll find a link to Patreon in the show description. I hope you'll take a moment to check it out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight our relaxation continues with more from a fundamental text of science, The Principles of Chemistry by Dmitri Mendeleev, translated from the Russian 6th edition by George Kamensky, ARSM, of the Imperial Mint St. Petersburg, member of the Russian Physico-Chemical Society, and edited by T.A. Lawson, BSc, Ph.D., Examiner in Coal Tar Products to the City and Guilds of London, and Institute Fellow of the Institute of Chemistry. First published in 1897 by Longmans Green & Co., 39 Paternoster Row, London. Let's pick up right where we left off, in the middle of Chapter 1, on water and its compounds. Let's begin. Although in the majority of cases the solubility of solids increases with the temperature, yet there are some solid substances whose solubilities decrease on heating. Glauber's salt, or sodium sulfate, forms a particularly instructive example of the case in question. If this salt be taken in an ignited state, deprived of its water of crystallization, then its solubility in 100 parts of water varies with the temperature in the following manner. At 0 degrees, 5 parts of the salt form a saturated solution. At 20 degrees, 20 parts of the salt. At 33 degrees, more than 50 parts. The solubility, as will be seen, increases with the temperature, as is the case with nearly all salts. But starting from 33 degrees, it suddenly diminishes, and at a temperature of 40 degrees, less than 50 parts of the salt dissolve. At 60 degrees, only 45 parts of the salt, and at 100 degrees, about 43 parts of the salt in 100 parts of water. This phenomenon may be traced to the following facts. Firstly, that this salt forms various compounds with water, as will be afterwards explained. Secondly, that at 33 degrees, the compound Na2SO4 plus 10H2O formed from the solution at lower temperatures melts. And thirdly, that on evaporation at a temperature above 33 degrees, an anhydrous salt, Na2SO4, separates out. It will be seen from this example how complicated such an apparently simple phenomenon as solution really is, and all data concerning solutions lead to the same conclusion. This complexity becomes evident in investigating the heat of solution. If solution consisted of a physical change only, then in the solution of gases there would be evolved, and in the solution of solids there would be absorbed, just that amount of heat corresponding to the change of state. But in reality, a large amount of heat is always evolved in solution, depending on the fact that in the process of solution, chemical combination takes place, accompanied by an evolution of heat. 17 grams of ammonia, this weight corresponds with its formula NH3, in passing from a gaseous into a liquid state, evolve 4,400 units of heat, latent heat. That is, the quantity of heat necessary to raise the temperature of 4,400 grams of water 1 degree. The same quantity of ammonia, in dissolving in an excess of water, evolves twice as much heat, namely 8,800 units, showing that the combination with water is accompanied by the evolution of 4,400 units of heat. Further, the chief part of this heat is separated in dissolving in small quantities of water, so that 17 grams of ammonia, in dissolving in 18 grams of water, this weight corresponds with its composition H2O, evolves 7,535 units of heat, and therefore the formation of the solution NH3 plus H2O evolves 3,135 units of heat beyond that due to the change of state. As in the solution of gases, the heat of liquefaction and of chemical combination with water are both positive. Therefore, in the solution of gases in water, a heat effect is always observed. This phenomenon is different in the solution of solid substances because their passage from a solid to a liquid state is accompanied by an absorption of heat, negative heat, whilst their chemical combination with water is accompanied by an evolution of heat, positive heat. Consequently, their sum may either be a cooling effect when the positive chemical portion of heat is less than the negative physical, or it may be, on the contrary, a heating effect. This is actually the case. 124 grams of sodium thiosulfate employed in photography, Na2S2O3 5H2O, in melting at 48 degrees, absorbs 9,700 units of heat, but in dissolving in a large quantity of water at the ordinary temperature, it absorbs 5,700 units of heat, which shows the evolution of heat, about positive 4,000 units, notwithstanding the cooling effect observed in the process of solution in the act of the chemical combination of the salt with water. But in most cases, solid substances in dissolving in water evolve heat, notwithstanding the passage into a liquid state, which indicates so considerable an evolution of positive heat in the act of combination with water that it exceeds the absorption of negative heat, dependent on the passage into a liquid state. Thus, for instance, calcium chloride, CaCl2, magnesium sulfate, MgSO4, and many other salts evolve heat in dissolving. For example, 60 grams of magnesium sulfate evolve about 10,000 units of heat. Therefore, in the solution of solid bodies, either a cooling or a heating effect is produced. According to the difference of the reacting affinities, when they are considerable, that is, when water is with difficulty separated from the resultant solution, and only with a rise of temperature, such substances absorb water vapor, then much heat is evolved in the process of solution, just as in many reactions of direct combination, and therefore a considerable heating of the solution is observed. Of such a kind, for instance, is the solution of sulfuric acid, oil of vitriol, H2SO4, and of caustic soda, NaHO, etc., in water. Solution is a reversible reaction, for if the water be expelled from a solution, the substance originally taken is obtained again, but it must be borne in mind that the expulsion of the water taken for solution is not always accomplished with equal facility, because water has different degrees of chemical affinity for the substance dissolved. Thus, if a solution of sulfuric acid, which mixes with water in all proportions, be heated, it will be found that very different degrees of heat are required to expel the water. When it is in a large excess, water is given off at a temperature slightly above 100 degrees, but if it be in but a small proportion, there is such an affinity between it and the sulfuric acid that at 120 degrees, 150 degrees, 200 degrees, and even at 300 degrees, water is still retained by the sulfuric acid. The bond between the remaining quantity of water and the sulfuric acid is evidently stronger than the bond between the sulfuric acid and the excess of water. The force acting in solutions is consequently of different intensity, starting from so feeble an attraction that the properties of water, as for instance its power of evaporation, are but very little changed, and ending with cases of strong attraction between the water and the substance dissolved in or chemically combined with it. In consideration of the very important significance of the phenomena, and of the cases of the breaking up of solutions with separation of water, or of the substance dissolved from them, we shall further discuss them separately, after having acquainted ourselves with certain peculiarities of the solution of gases and of solid bodies. The solubility of gases, which is usually measured by the volume of gas at 0 degrees and 760 millimeters pressure per 100 volumes of water, varies not only with the nature of the gas and also of the solvent and with the temperature, but also with the pressure, because gases themselves change their volume considerably with the pressure. As might be expected, 1. Gases which are easily liquefied by pressure and cold are more soluble than those which are liquefied with difficulty. Thus, in 100 volumes of water, only 2 volumes of hydrogen dissolve at 0 degrees and 760 millimeters of pressure, 3 volumes of carbonic oxide, 4 volumes of oxygen, etc., for these are gases which are liquefied with difficulty, whilst there dissolve 180 volumes of carbonic anhydride, 130 of nitrous oxide, and 437 of sulfurous anhydride, for these are gases which are rather easily liquefied. 2. The solubility of a gas is diminished by heating, which is easily intelligible from what has been said previously. The elasticity of a gas becomes greater. It is removed further from a liquid state. Thus 100 volumes of water at 0 degrees dissolve 2.5 volumes of air, and at 20 degrees only 1.7 volume. For this reason, cold water, when brought into a warm room, parts with a portion of the gas dissolved in it. 3. The quantity of the gas dissolved varies directly with the pressure. This rule is called the law of Henry and Dalton, and is applicable to those gases which are little soluble in water. Therefore, a gas is separated from its solution in water in a vacuum, and water saturated with a gas under great pressure parts with it if the pressure be diminished. Thus many mineral springs are saturated underground with carbonic anhydride under the great pressure of the column of water above them. On coming to the surface, the water of these springs boils and foams on giving up the excess of dissolved gas. Sparkling wines and aerated waters are saturated under pressure with the same gas. They hold the gas so long as they are in a well-corked vessel. When the cork is removed and the liquid comes in contact with air at a lower pressure, part of the gas, unable to remain in solution at a lower pressure, is separated as froth, with the hissing sound familiar to all. It must be remarked that the law of Henry and Dalton belongs to the class of approximate laws, like the laws of gases, Gay-Lussac's and Marriott's, and many others. That is, it expresses only a portion of a complex phenomenon, the limit towards which the phenomenon aims. The matter is rendered complicated from the influence of the degree of solubility and of affinity of the dissolved gas for water. Gases which are little soluble, for instance hydrogen, oxygen, and nitrogen, follow the law of Henry and Dalton the most closely. Carbonic anhydride exhibits a decided deviation from the law, as is seen from the determinations of Wroblewski, 1882. He showed that at 0 degrees, a cubic centimeter of water absorbs 1.8 cubic centimeter of the gas under a pressure of 1 atmosphere. Under 10 atmospheres, 16 cubic centimeters, and not 18, as it should be according to the law. Under 20 atmospheres, 26.6 cubic centimeters, instead of 36, and under 30 atmospheres, 33.7 cubic centimeters. However, as the researches of Sekhanov show, the absorption of carbonic anhydride within certain limits of change of pressure and at the ordinary temperature by water and even by solutions of salts which are not chemically changed by it or do not form compounds with it, very closely follows the law of Henry and Dalton, so that the chemical bond between this gas and water is so feeble that the breaking up of the solution with separation of the gas is accomplished by a decrease of pressure alone. The case is different if a considerable affinity exists between the dissolved gas and water. Then it might even be expected that the gas would not be entirely separated from water in a vacuum, as should be the case with gases according to the law of Henry and Dalton. Such gases, and in general all those which are very soluble, exhibit a distinct deviation from the law of Henry and Dalton. As examples, ammonia and hydrochloric acid gas may be taken. The former is separated by boiling and decrease of pressure, while the latter is not, but they both deviate distinctly from the law, as shown in the following table. It will be remarked, for instance, from this table, that whilst the pressure increased 10 times, the solubility of ammonia only increased 4½ times. A number of examples of such cases of the absorption of gases by liquids might be cited, which do not in any way, even approximately, agree with the laws of solubility. Thus, for instance, carbonic anhydride is absorbed by a solution of caustic potash in water, and if sufficient caustic potash be present, it is not separated from the solution by a decrease of pressure. This is a case of more intimate chemical combination. A correlation less completely studied, but similar and clearly chemical, appears in certain cases of the solution of gases in water, and we shall afterwards find an example of this in the solution of hydrogen iodide. But we will first stop to consider a remarkable application of the law of Henry and Dalton in the case of a solution of a mixture of two gases, and this we must do all the more because the phenomena which there take place cannot be foreseen without a clear theoretical representation of the nature of gases. The law of partial pressures is as follows. The solubility of gases in intermixture with each other does not depend on the influence of the total pressure acting on the mixture, but on the influence of that portion of the total pressure which is due to the volume of each given gas in the mixture. Thus, for instance, if oxygen and carbonic anhydride were mixed in equal volumes and exerted a pressure of 760 millimeters, then water would dissolve so much of each of these gases as would be dissolved if each separately exerted a pressure of half an atmosphere. And in this case, at 0 degrees, 1 cubic centimeter of water would dissolve 0.02 cubic centimeter of oxygen and 0.90 cubic centimeter of carbonic anhydride. If the pressure of a gaseous mixture equals H, and in N volumes of the mixture there will be A volumes of a given gas, then its solution will proceed as though this gas were dissolved under a pressure H times A over N, that portion of the pressure under influence of which the solution proceeds is termed the partial pressure. In order to clearly understand the cause of the law of partial pressures, an explanation must be given of the fundamental properties of gases. Gases are elastic and disperse in all directions. We are led from what we know of gases to the assumption that these fundamental properties of gases are due to a rapid progressive motion in all directions which is proper to their smallest particles, molecules. These molecules, in impinging against an obstacle, produce a pressure. The greater the number of molecules impinging against an obstacle in a given time, the greater the pressure. The pressure of a separate gas or of a gaseous mixture depends on the sum of the pressures of all the molecules, on the number of blows in a unit of time on a unit of surface, and on the mass and velocity or the vis viva of the impinging molecules. The nature of the different molecules is of no account. The obstacle is acted on by a pressure due to the sum of their vis viva. But in a chemical action, such as the solution of gases, the nature of the impinging molecules plays, on the contrary, the most important part. In impinging against a liquid, a portion of the gas enters into the liquid itself and is held by it so long as other gaseous molecules impinge against the liquid. As regards the solubility of a given gas, for the number of blows it makes on the surface of a liquid, it is immaterial whether other molecules of gases impinge side by side with it or not. Hence the solubility of a given gas will be proportional, not to the total pressure of a gaseous mixture, but to that portion of it which is due to the given gas separately. Moreover, the saturation of a liquid by a gas depends on the fact that the molecules of gases that have entered into a liquid do not remain at rest in it, although they enter in a harmonious kind of motion with the molecules of the liquid, and therefore they throw themselves off from the surface of the liquid, just like its vapor if the liquid be volatile. If in a unit of time an equal number of molecules penetrate into, leap into a liquid, and leave or leap out of a liquid, it is saturated. It is a case of mobile equilibrium and not of rest. Therefore, if the pressure be diminished, the number of molecules departing from the liquid will exceed the number of molecules entering into the liquid, and a fresh state of mobile equilibrium only takes place under a fresh equality of the number of molecules departing from and entering into the liquid. In this manner the main features of the solution are explained, and furthermore of that special chemical attraction, penetration and harmonious motion of a gas for a liquid, which determines both the measure of solubility and the degree of stability of the solution produced. The consequences of the law of partial pressures are exceedingly numerous and important. All liquids in nature are in contact with the atmosphere, which, as we shall afterwards see more fully, consists of an intermixture of gases, chiefly four in number: oxygen, nitrogen, carbonic anhydride, and aqueous vapor. 100 volumes of air contain approximately 78 volumes of nitrogen and about 21 volumes of oxygen. The quantity of carbonic anhydride by volume does not exceed 0.05. Under ordinary circumstances, the quantity of aqueous vapor is much greater than this, but it varies, of course, with climatic conditions. We conclude from these numbers that the solution of nitrogen in a liquid in contact with the atmosphere will proceed under a partial pressure of 78/100 times 760 millimeters, if the atmospheric pressure equals 760 millimeters. Similarly, under a pressure of 600 millimeters of mercury, the solution of oxygen will proceed under a partial pressure of about 160 millimeters, and the solution of carbonic anhydride only under the very small pressure of 0.4 millimeters. As, however, the solubility of oxygen in water is twice that of nitrogen, the ratio of oxygen to nitrogen dissolved in water will be greater than the ratio in air. It is easy to calculate what quantity of each of the gases will be contained in water, and taking the simplest case, we will calculate what quantity of oxygen, nitrogen, and carbonic anhydride will be dissolved from air having the above composition at 0 degrees and 760 millimeters pressure. Under a pressure of 760 millimeters, 1 cubic centimeter of water dissolves 0.0203 cubic centimeter of nitrogen, or under the partial pressure of 600 millimeters, it will dissolve 0.0203 by 600/700ths, or 0.0160 cubic centimeter. Of oxygen, 0.0411 times 160/760ths, or 0.0086 cubic centimeter. Of carbonic anhydride, 1.8 times 0.4760th, or 0.00095 cubic centimeter. Hence, 100 cubic centimeters of water will contain at 0 degrees altogether 2.55 cubic centimeters of atmospheric gases, and 100 volumes of air dissolved in water will contain about 62% of nitrogen, 34% of oxygen, and 4% of carbonic anhydride. The waters of rivers, wells, etc. usually contains more carbonic anhydride. This proceeds from the oxidation of organic substances falling into the water. The amount of oxygen, however, dissolved in water appears to be actually about 1/3 the dissolved gases, whilst air contains only 1/5 of it by volume. According to the law of partial pressures, whatever gas be dissolved in water will be expelled from the solution in an atmosphere of another gas. This depends on the fact that gases dissolved in water escape from it in a vacuum because the pressure is nil. An atmosphere of another gas acts like a vacuum on a gas dissolved in water. Separation then proceeds because the molecules of the dissolved gas no longer impinge upon the liquid and are not dissolved in it, and those previously held in solution leave the liquid in virtue of their elasticity. For the same reason, a gas may be entirely expelled from a gaseous solution by boiling, at least in many cases when it does not form particularly stable compounds with water. In fact, the surface of the boiling liquid will be occupied by aqueous vapor, and therefore all the pressure acting on the gas will be due to the aqueous vapor. On this account, the partial pressure of the dissolved gas will be very inconsiderable, and this is the sole reason why a gas separates from a solution on boiling the liquid containing it. At the boiling point of water, the solubility of gases in water is still sufficiently great for a considerable quantity of a gas to remain in solution. The gas dissolved in the liquid is carried away, together with the aqueous vapor. If boiling be continued for a long time, all the gas will finally be separated. It is evident that the conception of the partial pressures of gases should be applied not only to the formations of solutions, but also to all cases of chemical action of gases. Especially numerous are its applications to the physiology of respiration, for in these cases it is only the oxygen of the atmosphere that acts. The solution of solids, whilst depending only in a small measure on the pressure under which solution takes place, because solids and liquids are almost incompressible, is very clearly dependent on the temperature. In the great majority of cases, the solubility of solids in water increases with the temperature. And further, the rapidity of solution increases also. The latter is determined by the rapidity of diffusion of the solution formed into the remainder of the water. The solution of a solid in water, although it is, as with gases, a physical passage into a liquid state, is determined, however, by its chemical affinity for water. This is clearly shown from the fact that in solution there occurs a diminution in volume, a change in the boiling point of water, a change in the tension of its vapor, in the freezing point, and in many similar properties. If solution were a physical and not a chemical phenomenon, it would naturally be accompanied by an increase and not a diminution of volume, because generally in melting, a solid increases in volume, its density diminishes. Contraction is the usual phenomenon accompanying solution and takes place even in the addition of solutions to water and in the solution of liquids in water, just as happens in the combination of substances when evidently new substances are produced. The contraction which takes place in solution is, however, very small, a fact which depends on the small compressibility of solids and liquids, and on the insignificance of the compressing force acting in solution. The change of volume which takes place in the solution of solids and liquids, or the alteration in specific gravity corresponding with it, depends on peculiarities of the dissolving substances and of water, and in the majority of cases is not proportional to the quantity of the substance dissolved, showing the existence of a chemical force between the solvent and the substance dissolved, which is of the same nature as in all other forms of chemical reaction. The feeble development of the chemical affinities acting in solutions of solids becomes evident from those multifarious methods by which their solutions are decomposed, whether they are saturated or not. On heating, absorption of heat, on cooling, and by internal forces alone, aqueous solutions in many cases separate into their components or their definite compounds with water. The water contained in solutions is removed from them as vapor, or by freezing in the form of ice. But the tension of the vapor of water held in solution is less than that of water in a free state, and the temperature of the formation of ice from solutions is lower than 0 degrees. Further, both the diminution of vapor tension and the lowering of the freezing point proceed in dilute solutions almost in proportion to the amount of a substance dissolved. Thus, if per 100 grams of water there be in solution 1, 5, 10 grams of common salt, NaCl, then at 100 degrees the vapor tension of the solutions decreases by 4, 21, 43 millimeters of the barometric column against 760 millimeters, or the vapor tension of water, whilst the freezing points are negative 0.58 degrees, negative 2.91 degrees, and negative 6.10 degrees respectively. The above figures are almost proportional to the amounts of salt in solution, 1, 5, and 10 per 100 of water. Furthermore, it has been shown by experiment that the ratio of the diminution of vapor tension to the vapor tension of water at different temperatures in a given solution is an almost constant quantity, and that for every dilute solution, the ratio between the diminution of vapor tension and of the freezing point is also a tolerably constant quantity. The diminution of the vapor tension of solutions explains the rise in boiling point due to the solution of solid, non-volatile bodies in water. The temperature of a vapor is the same as that of the solution from which it is generated, and therefore it follows that the aqueous vapor given off from a solution will be superheated. A saturated solution of common salt boils at 108.4 degrees. A solution of 335 parts of niter in 100 parts of water at 115.9 degrees, and a solution of 325 parts of potassium chloride in 100 parts of water at 179 degrees, if the temperature of ebullition be determined by immersing the thermometer bulb in the liquid itself. This is another proof of the bond which exists between water and the substance dissolved, and the bond is seen still more clearly in those cases. For example, in the solution of nitric or formic acid in water, where the solution boils at a higher temperature than either water or the volatile substance dissolved in it. For this reason, the solutions of certain gases, for instance, hydriodic or hydrochloric acid, boil above 100 degrees. The separation of ice from solutions explains both the phenomenon, well known to sailors, that the ice formed from salt water gives fresh water, and also the fact that by freezing, just as by evaporation, a solution is obtained which is richer in salts than before. This is taken advantage of in cold countries for obtaining a liquor from sea water, which is then evaporated for the extraction of salt. On the removal of part of the water from a solution by evaporation or the separation of ice, a saturated solution should be obtained, and then the solid substance dissolved should separate out. Solutions saturated at a certain temperature should also separate out a corresponding portion of the substance dissolved if they be reduced by cooling to a temperature at which the water can no longer hold the former quantity of the substance in solution. If this separation, by cooling a saturated solution or by evaporation, take place slowly, crystals of the substance dissolved are in many cases formed, and this is the method by which crystals of soluble salts are usually obtained. Certain solids very easily separate out from their solutions in perfectly formed crystals, which may attain very large dimensions. Such are nickel sulfate, alum, sodium carbonate, chrome alum, copper sulfate, potassium ferricyanide, and a whole series of other salts. The most remarkable circumstance in this is that many solids, in separating out from an aqueous solution, retain a portion of water, forming crystallized solid substances which contain water. A portion of the water previously in the solution remains in the separated crystals. The water which is thus retained is called the water of crystallization. Alum, copper sulfate, Glauber's salt, and magnesium sulfate contain such water, but neither sal ammoniac, table salt, niter, potassium chlorate, silver nitrate, nor sugar contains any water of crystallization. One and the same substance may separate out from a solution with or without water of crystallization, according to the temperature at which the crystals are formed. Thus, common salt, in crystallizing from its solution in water, at the ordinary or at a higher temperature, does not contain water of crystallization. But if its separation from the solution takes place at a low temperature, namely below -5 degrees, then the crystals contain 38 parts of water in 100 parts. Crystals of the same substance which separate out at different temperatures may contain different amounts of water of crystallization. This proves to us that a solid dissolved in water may form various compounds with it, differing in their properties and composition and capable of appearing in a solid, separate form, like many ordinary definite compounds. This is indicated by the numerous properties and phenomena connected with solutions, and gives reason for thinking that there exist in solutions themselves such compounds of the substance dissolved, and the solvent or compound similar to them, only in a liquid, partly decomposed form. Even the color of solutions may often confirm this opinion. Copper sulfate forms crystals having a blue color and containing water of crystallization. If the water of crystallization be removed by heating the crystals to redness, a colorless anhydrous substance is obtained, a white powder. From this it may be seen that the blue color belongs to the compound of the copper salt with water. Solutions of copper sulfate are all blue, and consequently they contain a compound similar to the compound formed by the salt with its water of crystallization. Crystals of cobalt chloride, when dissolved in an anhydrous liquid, like alcohol for instance, give a blue solution, but when they are dissolved in water, a red solution is obtained. Crystals from the aqueous solution, according to Professor Potilitsyn, contain 6 times as much water, CoCl2 6H2O, for a given weight of the salt, as those violet crystals, CoCl2 1H2O, which are formed by the evaporation of an alcoholic solution. That solutions contain particular compounds with water is further shown by the phenomena of supersaturated solutions, of so-called cryohydrates, of solutions of certain acids having constant boiling points, and the properties of compounds containing water of crystallization, whose data it is indispensable to keep in view in the consideration of solutions. And with that hint of riveting topics to come, I think we'll end this evening's reading from The Principles of Chemistry, Volume 1, by Dmitri Mendeleev. That was a lot of information about solutions, but I did enjoy the part about sparkling wines. I hope you enjoyed that as well. If you'd like to read this classic work for yourself, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.